Okay. Like most things in calculus, the development of a calculus idea usually comes from a geometric fact. So let's take something we know, we may not work with all the time. I've got a circle, and if I go from the center out, this is called a central angle. Get a better new pen here. That's called a central angle. We know that's the radius. This piece right here has length. We usually say S. S being the arc length variable, and it has area A. If I have a circle and this is from the center, this creates 3 equal ratios. Now we use these all throughout calculus to derive formulas. And basically it's like saying this. Let's say that I took a quarter of the circle. Well, then I should have a quarter of the angle, a quarter of the area, a quarter of the arc length. So in other words, theta is to the angle all the way around, which would be 2 pi radians, as A is to the entire area, which is pi r squared, as S is to the entire circumference, which is 2 pi r. Now we're very familiar with these. If I put any 2 ratios together, that's what's called a proportion. That's the definition of a proportion, 2 equal ratios. So if I put any 2 of them together, I can generate a formula. For example, putting the last 2 together, this is how we were able to come up with the surface area formula in Calc 1. Okay, you may have not remembered that. But if I put the first 2 together, then A would equal theta over 2 pi times pi r squared, which would simply give us 1/2 r squared theta. And that's a very, very powerful formula. Now, does anybody know what this pi-shaped wedge is actually called? It actually has a formal name. I'm just curious. Anybody want to try it?
Sector.
Sector, good. That's called a sector of a circle. It's not an arbitrary, arbitrary chunk. It has to come from the center. So if I just slice, when you're cutting the cake or cutting the pie, you always get annoyed when the person doesn't make the cut directly in the center because all the pieces are going to be all off, and you'll probably get a smaller piece as a result, right? Those are sectors. All right, now with that, that's key. Now, going back to Calc 1 for a moment, revisit Calc 1 just for a second. Okay, I've got, really simple. I've got a region in the XY plane. And what we did was we subdivided it into an arbitrary number of rectangles of varying widths. We took any place within the rectangle and squared it off. Right? We did stuff like this. And then we said, if we add up the area of each of those rectangles, that is a reasonable estimator of the area under the curve. So if this was x0 and that's x1 and so on, and then that's xn, that's the nth one, then let's say that's the ith one. So what we did in Calc 1, we said the area of the ith rectangle equals, okay, now that would be xi minus 1, that would be xi, right? The first rectangle goes from x0 to x1, the second goes from x1 to x2, and so on. The ith one goes from xi minus 1 to xi. If I take that height, which we generally called wi, where wi was between xi minus 1 and xi, then I said that area was the height of f of wi. Now, w could be any value between here and here. And that's where I'm calculating the height. I could use the left, the right, or anywhere in between, times delta xi, which would be the difference of these two. Okay, we say the overall area could be estimated by the sum from 1 to n of these guys. This should look familiar. And the area equals the limit as the norm of the partition approaches 0 of that sum. This should all be very familiar because this is the foundation of basically how you went from here to the fundamental theorem. This is called a Riemann sum. But this is a Riemann sum for a rectangular coordinate system. We now know this is equal to the definite integral from a to b f of x dx. Okay, that was the whole lineage, the whole development of area under this curve, eventually getting us to here. That's wonderful. But what if? What if my integrand is not something I can easily integrate? In other words, what if my integrand involves things with circles? What if my boundary involves things more or less circular? So let me give you a different picture. So what if my region looked more like this? This is my region. Clearly, I'm not bound by y equal a function of x. I'm bound by something a bit more complicated. Let's say that this angle, let's say that's theta 1, and let's say that angle is theta 2, for lack of a better name. I would like to find this area, but I cannot do the same Riemann sum. Putting rectangles will not be useful because my boundaries are changing, right? My boundaries here are different than my boundaries here. Oh, but what if instead I said, let's consider, I'm going to erase, I don't need this. Erase that picture for a moment. Like this. And instead of rectangles, what if we kind of see little curves here? Instead of rectangles, what if I made sectors? What if I made sectors of a circle? Now, by the way, each of these come from a different size circle because where I rounded them off would be different. But this is a piece of a bigger circle, right? This one here's a piece of a bigger circle. But what if I found each of those individual areas and I added those up? That would be a reasonable estimator. So let's figure out what is the area of one of them. So first thing I need to do is I need to rewrite this not in XY world, but in R theta world. So now let's consider R is actually a function of theta. Okay. Then this here and this here are the same R. That's exactly the same R because they're parts of the same sector of the circle. So with that said, I want to find this area. Well, remember what we did before. We said it was 1/2 R squared theta. But this would be, I subdivided this. So this technically, this one here, I guess, this would be delta theta 1. And the next one would be delta theta 2, and so on. So let's call this one the ith sector. So the area of my ith sector, I keep pulling the bad pen up, would be 1/2 the ith R squared times delta theta I. That little width, but that's my angle. This would be the ith, so that'd be delta theta 1, delta theta 2, and so on. Oh, okay. Then I can say that my area can be reasonably estimated by, because I have n of them. This looks kind of familiar. Can I do the Riemann sum here? Yes. In this case, the norm of the partition would be the largest such delta theta. So area would equal the limit as the norm of the partition approaches 0. The norm of the partition, remember, is the largest such slice or partition. In this case, they would be thetas. Before it would be delta x's. And I know this translates directly into an integral. But what integral? Well, the integral from, I said we called that theta 1 and we called that theta 2. Of what? Of 1/2 R squared. Remember, that's R of theta. So in fact, it'd probably be better if I wrote like this. R of theta squared d theta. And this is the formula for finding area using polar coordinates. Again, all I'm doing is using the fact that I already know how to find the area of a sector, because for the Riemann sum, we used the fact that we knew how to find the area of a rectangle, base times height. My base happened to be my delta x. My height happened to be my f of x. In this case, it's the 1/2 R squared theta, but these little delta thetas. So let's do an example of this from beginning to end. So this is a very powerful formula. We will use this formula next semester, and we'll use it in 3 dimensions as well. It's a very useful tool. Now, you don't just change something to polar in order to change it to polar. You change it to polar because the region you're integrating either is circular in nature, or you've got sine, you've got an integrand with x squared plus y squareds to various powers, things of that nature in 3D. You just basically, you have a complicated problem, right? If I've got x squared plus y squared, that is r squared. So let's consider, let's see. Let's do, I'm going to do something we did last day. Let's suppose we're considering r equals 4 cos theta. I think we did that one last day. Okay, we deemed, there we go. We knew what this one was. We knew this is a circle of radius 2. If you guys remember this, and it was centered at 2, 0. So we're gonna cheat. We already know how to find the area of a circle. That's not the point. I want to integrate to find this area using polar coordinates. Okay, so my integrand has to be 1/2 r squared times delta theta. So let's start with the 1/2 r squared. That would be 1/2 times 4 cos theta quantity squared, or 8 cos squared theta. Now remember, you cannot integrate a sine squared or a cos squared. You have to use your double angle formulas. So I'll remind you, I mean, those are things you really do at this point in your life. You want to know, but the cosine squared of theta we know is 1/2 1 plus cosine of 2 theta. Yeah. And sine squared is 1/2 of 1 minus cosine of 2 theta. That's a terrible looking theta. Okay, so I need to change this to this because, again, I can integrate cosine of 2 theta. I can't integrate cos squared, not without that substitution. So this will become 8 times 1/2 times 1 plus times cosine of 2 theta, and I'll go ahead and distribute. So that will be 4 plus 4 cos 2 theta. I can now say my area equals, okay, hang on a second. I got to tone down some of the outside noise here. So I'm going to integrate this. Now there's still one major piece that we need. Anybody want to help me out here? What do we still need? Haven't even referred to it yet. What do we need here?
The limits of the integral?
Yeah, limits of integration. Yeah. Is it 0 to 2 pi? Normally people would say, yeah, it's 0 to 2 pi. It's not always 0 to 2 pi. In fact, we did this problem last day, if you remember. What did it take for me to complete the whole circle when we drew it? Do you guys remember? Because we did this one specifically last day.
0 to pi.
0 to pi. When theta is 0, I'm here. When theta was pi over 2, I was here. When theta was back to pi, I was here. We completed this circle from 0 to pi. If I integrate from 0 to 2 pi, basically I'm going to get twice as much area, and that would be incorrect. And by the way, the reason I chose something we already know what the area is, pi r squared, it's an easy way for us to verify this, that we're actually doing it correctly. Things that are centered at the origin, generally it's going to be 0 to 2 pi. Generally, again, there are exceptions, but if it's centered at the origin, it's probably 0 to 2 pi because you got to go all the way around. But this is centered over here. So it completed 0 to pi. Now let's integrate this. So this would be 4 theta plus or minus. Guys, walk me through it. Plus or minus. Antiderivative of 4 cosine 2 theta. Okay, I'll do my part. I'll do my part. My part is to put that. What goes here? Plus or minus, first of all. Let's see. Well, the derivative of
Plus.
So it should be plus. And is it times 1/2 or times 2?
2 sine 2 theta.
Yeah, times 1/2. Because when I differentiate, boom. Okay, good. That's one that we, oh gosh, I hate those kind, but that wasn't that bad. Okay, so what do we got here? We've got 4 pi plus 2 times the sine of 2 pi minus 0 plus 2 times the sine of 0. Well, I kind of like this one. You know why? That's 0, that's 0, and that's 0. So my answer is 4 pi. What is the area of a circle of radius 2? Pi times 2 squared. So we know we did it right. And by the way, that's also the confirmation that we knew those limits. Had I used limits of 0 to 2 pi, we would have gotten 8 pi as an answer. And you would say, wait a minute, that's not right. Now, I chose a very simple example because we already knew how to do it. Great. Now let's choose one we don't know how to do. All right. Let's do a cardioid. And I'll use the same ones we did last day, just to make it easier, because we already drew this last day. I believe, actually help me out. I don't remember. What coefficient did I use? I used sine. Did I use 4?
4 minus 4 sine theta.
Yeah. I want to use the same one because we already knew what it looked like. So, no. Sorry, this is upside down. Sorry, the other way. Yeah, I have a hard time drawing. I'm trying to make it look symmetric. My apologies. Yeah, that's better. That's way better. Okay. It's easier for me to draw it and then put in the axes. So it looks something like this. It's not drawn to scale. That's not really a big deal. So I want to find this area. So now here's the thing. Where do I start from? Well, at 0, okay, when theta is 0, r is 4. So that's supposed to be 4 units. Again, it says not drawn to scale. It's a little bit fatter. In fact, let me make it a little bit more to scale. Probably more like this. Okay. Yeah, okay, that's a little better. Sorry. I want it all to make sense. All right. That's probably more to scale than my first one. That's 4 units out. And then when I'm at pi over 2, this says I'm 0 units out. And then I keep going. Eventually, when I'm at 3 pi over 2, I'd have 4 minus 4 times -1. That puts me way down here, right, 8 units away, and so on. So when I'm measuring this thing, how do I decide what my R is? Well, here's how you do it. You always do your R the same way. You go from the origin out. See, there's my R. I could have also done this. Okay, there's my R. My R will always be the edge of my shape. Okay. In the previous example, just so you know, I'll go back to my previous problem. I select my R by starting here, and I go like this. And you notice that my wedge, my R is always the circle. Well, why is that important? Because we're going to talk about what happens if you have 2 shapes and they overlap or they intersect. Oh, okay, my boundaries can change. My boundaries here always were origin to outer edge of circle. My boundary here is always origin to outer edge of cardioid. That's really, really important if I'm trying to figure this out. Now, this thing also took 0 to 2 pi to complete. So I just need the 1/2 r squared. So I need to do this. Now, always do the algebra before you write the integral. You don't really want to write the integral of this and then do all your simplifying. So you write integral equals integral equals integral equals integral, and you haven't started to integrate yet. Do all your algebra. Then when you write your integral, the next thing you write would be your antiderivative. So when I square this, 16 times 1/2 and minus 32 times 1/2 plus 16 sine squared times 1/2. So now I need to replace the sine squared. Okay. Right here, that's going to be 4 minus 4 cos 2 theta. So now putting everything together, this will be 12 minus 16 sine theta minus 4 times the cosine of 2 theta. That's what the square of 1/2 the square of this will look like. So this will become my integrand. So let's go ahead, lop off some of this. So my area is the integral from 0 to 2 pi of this. Okay, now this, everything was about coming up with this integral. This should actually be really, really simple to integrate, but coming up with this, there's no way you could have looked at this and seen this. You had to do some work. So now my antiderivative, 12 theta minus 16 sine, so plus 16 cosine, minus 4 cos, so minus 2 sine, 2 theta. And again, generally speaking, when you have sines and cosines and you're going from 0 to 2 pi, generally you're going to get 0. And here's why. Because the cosine of 2 pi equals the cosine of 0. The sine of 4 pi equals the sine of 0. In both cases, it's 0. The only time you're not going to easily get 0 is if you have, let's say, like a half theta or something. So this is beautiful because this is going to be the same value at both ends. This is the same at both ends. So after all of that, my answer is simply going to be 24 pi. That's very nice. Now, you said, that wasn't that hard. I can do this in general. Does it ever get complicated? Oh, yes. Let's suppose for a moment that you wanted, let's say you just wanted this area right here. I only want that area right there. How would I do that? Well, remember, you're always going from the center, going from the origin out. So if I go from the origin out, I'm still going, my outer region is still this, but it's not going to be from 0 to 2 pi. I only want that piece, or I could say I want both pieces. By the way, the easiest way to do both pieces is to do one and just double it, but because it's symmetric. But if I only want that piece, what would my limits of integration be? Anybody want to try that?
0 to pi over 2.
0 to pi over 2. Good, because we said 0, I'm here, pi over 2, I'm here. I'm going to change, I just want that piece right there. So how does that change in this problem? I'm going to do a new problem now. And this is now pi over 2. And by the way, all of this was still absolutely necessary. What I'm changing now is I just want a smaller piece. Now, before I even finish, do you all agree that the answer to this question ought to be a lot smaller than the answer to this question? I'm just taking a teeny piece of it. It should be a small fraction in comparison. So let's see where this gets us. Okay, I don't think I'm going to get 24 pi anymore as an answer. All right, so when I evaluate this at pi over 2, that's going to give me 6 pi plus 16 times the cosine of pi over 2 minus 2 times the sine of pi minus, now evaluated at 0, 0 plus 16 times the cosine of 0 minus 2 times the sine of 0. So before you automatically start calling everything 0, there are a lot of zeros. That's 0, that's 0, that's a 0, that's a 0, that's not 0. Ooh, what is this? Anybody? What is that?
16.
That's 16. And that was a minus. That means this answer is 6 pi minus 16. Now, just to give you some perspective, the whole cardioid was 24 pi. 24 pi is approximately the whole thing, about approximately 75.4. I wanted this tiny little piece right there, and we got this. That's approximately about 2.8. Oh, that's tiny in comparison. Yeah, and it should be. What if I only wanted the part below the x-axis? I could do that. I just changed my limits. What if I only wanted those two pieces? I can do that. I just changed my limits. If I only want a portion of it, I just change the limits so that it is appropriate. Okay, that's it. Now, I want to take the same problem, but now I want to do something a little more complicated. We already have all this. So I'm going to leave that there for a moment. So let's do a what if. Draw a new picture. I want find the area that is inside of this and outside r equal 4. Now, just so you know, r equal a constant. R equal a constant. What would r equal a constant be? Anybody know what shape that is? Always. Remember, you're starting from the origin and you want all the points that are exactly 4 units from the origin. What would that have to be?
It's a circle.
Circle of radius 4 from the origin. Oh, that's it. If, by the way, here's how you can work backwards. If r equals 4, then doesn't that mean that r squared is 4 squared? And isn't r squared x squared plus y squared? Is that a no duh? Circle of radius 4 centered at the origin? Yeah, r equal a constant. By the way, it has to be a non-negative number. R equal a constant is a circle of that radius, always. That's why r equal a negative number doesn't make sense. That no work. All right. So I want to find, said outside the circle, inside the cardioid. I'll do my best to try to make this kind of accurate. You notice I picked 4. It was very important that I picked 4. And this is a fairly accurate graph. Okay, so I'm outside the circle, inside the cardioid. So I actually am asking for this area out here. Oh, by the way, I could have said inside the circle, outside the cardioid. That'd be up here. I could have said inside both the circle and the cardioid. That'd be that part right there. I could change the questions. What would change is obviously my integrand and also perhaps my limits of integration. So there's a couple of things. And by the way, the nice thing is the 4 was strategic. And here's why. I need to figure out where these intersect actually. So where they intersect is when 4 equals 4 minus 4 sine theta. That will happen when what? 0 equals negative 4 sine theta. That means that sine theta has to equal 0. When is sine theta equal to 0? When theta is 0 or when theta is pi. Okay, so that corresponds with my picture exactly. That is huge. So if that's 0, that was pi over 2, that's pi, then that means this must be from pi to 2 pi. And that's important. So my limits of integration are going to be from pi to 2 pi to capture this portion. Let's say I wanted this top piece. These limits would be from 0 to pi. Okay, that's the big difference. Now, how do I do this? Well, again, go back to Calc 1 for a minute. In Calc 1, this is like beginning. I want to find the area bounded by these 2 curves. Now I know how to find the area under a curve, but how do I find this one? Well, in Calc 1, didn't you say, let me just take the big area and subtract out the small area? Isn't that what we did? Oh, so it ended up being the integral of f minus g. So what do I want to do here? I want to take the area of the cardioid and then subtract out the stuff underneath it, which would be equivalent to say, I want the area of the big sector minus the area of the little sector. That's it. Big area minus little area. So that's exactly what we did before. But unlike the rectangles, I'm not subtracting rectangles, I'm subtracting 1/2 r squareds. Oh, okay, so I'm going to take this 1/2 r squared and I'm going to subtract this 1/2 r squared. And then that's going to be my new integrand. Okay, so let's do that. Again, big sector, so it's 1/2 this guy squared minus little sector. That gives me the stuff in between. That's always what you're going to do when you're trying to find between. So I want to find 1/2 4 minus 4 sine theta quantity squared minus 1/2 4 squared. Whatever that is going to be my integrand. So this was before, so that was 8 minus 16 sine theta plus 8 sine squared theta minus 8. Oh, I see. That's a little bit simpler, perhaps. So my new integrand is going to be this. I'm not going from 0 to 2 pi. We deemed we're going to go from pi to 2 pi. Now, I still need to use my double angle formula. So negative 16 sine theta plus 8 times 1/2, 1 minus cosine 2 theta. So that's 4 minus 4 cos 2 theta. So altogether, I have 4 minus 16 sine theta minus 4 cos 2 theta. That's kind of an interesting integrand. I got a lot of negatives. Again, this plus this plus this. Now I can say that my area equals the integral of 4 minus 16 sine theta minus 4 times the cosine of 2 theta. We said from pi to 2 pi. Okay. So that's going to be 4 theta. The antiderivative of this would be plus 16 cos theta. Antiderivative, this would be minus 2 times the sine of 2 theta from pi to 2 pi. Now let's go ahead and evaluate. I'm not going to get all zeros this time. So that's 8 pi plus 16 times the cosine of 2 pi. The cosine of 2 pi is 1, so that should be plus 16, minus 2 times the sine of 4 pi, or sine of 4 pi, that's 0. Now evaluate it at pi. Aha, that would be 4 pi. Cosine of pi is negative 1. So this will be minus 16. And then again, that will be 0. Okay, so now let's look at that final answer. I didn't get all zeros, did I? So 8 pi minus 4 pi, that's 4 pi plus 32. 4 pi plus 32. Now, we knew what that piece was there. We just did it a moment ago. That's 1/2 of a circle, and now I've got this. Because we've already done a previous calculation, we can kind of compare. I'd kind of like to know, what is the area of this region? What is the area of this region? What is the area of these regions right here? Well, this is my answer. Now remember, the overall answer before was 24 pi, which is about, like I said, 75.4. How big is this answer? Again, so, it's, again, when I go to Home Depot later on today and I said, all right, I need 4 pi plus 32 inches of wood, they're going to be confused. I would like to know a decimal value. I don't know how big that is. So 4 pi plus 32 is about 44.5, a little more than 44.5. It's about. Okay. What did we say these were? What was it? It was
2.8 each.
No, but what was the in pi? It was
6 pi minus 16.
Okay, so that was 6 pi minus 16. That's 6 pi minus 16. That's 4 pi plus 32. And by the way, isn't this piece here exactly half the circle? That's the semicircle. That is a circle of radius 4. Now, a circle of radius 4 has area pi times 4 squared, or 8 pi, or excuse me, 16 pi. Do you all agree that this area here should therefore be 8 pi? Is everybody cool with that? That area has to be 8 pi because it's half of a circle of radius 4. Now, if I take that piece, plus that piece, plus that piece, plus that piece. So 6 plus 6 is 12, plus 8 is 20, plus 4, that's 24 pi. Negative 16 plus 32. There's my 24 pi. It worked. We didn't mess it up. As I say, if we messed up, it'd be partly your fault too. So we've just figured out a whole bunch of little pieces of this. By the way, can I also figure out that outer area? Sure. I would take this half circle and I would subtract those pieces. So you never have to keep redoing a problem one like this, because once you do pieces, you can do other pieces. So one of the problems that we do next semester is we'll take things like, let's take a sphere. Now let's remove a cone from the sphere, and how much volume in the cone, and then what about the volume around it? Well, once we find one thing, we can just use that answer over and over again to find the others. We don't always have to recalculate. Now, this is the last thing we learn in Calc 2. It's not the most complicated. The integrations are actually just sines and cosine. That's just not that bad, but it's a very different form. Now, we're done. There's no more new content. We have a final exam in 2 weeks, and between now and then, we have an exam, a couple of reviews, and other things. Now, I want to remind you, today you turned in quiz 23. That's the end of the material that the exam is going to cover. But I just did lecture 25, and last day was lecture 24. Those last 2 lectures will be on the last 2 quizzes. So that way, when you walk into the final exam, even if not everything's been on an exam, everything will at least have been on a quiz. Of the 25 lectures, 23 of them will have been on the first 3 exams. The last 2 lectures still are on the last 2 quizzes. So there is no mystery material, no unknown material for the final. So your next exam, again, is everything, well, basically since the last exam. I believe that's, in this case, I think it's 8 lectures, if I'm not mistaken. I think somebody told me that. Just look at your syllabus. What was the last quiz before the last exam? That's where that one ended. Now, what I want to do is we're going to take a break shortly, and then during the office time, basically, I want that to be the question and answer period. But let me remind you about the exam, the logistics. The exam starts at 11:10. I will email you the exam around 11, so that gives you time to print it or to write stuff down, get everything set. You may bring a non-graphing calculator, only scientific. It is very likely that you'll barely even use your calculator, but I'd like you to have a calculator because you are going to be doing some things, maybe a Taylor polynomial that you might have to raise a fraction to a power or something. I don't want you doing pencil and paper or perfect calculus, bad arithmetic. Have a cheap calculator. You can't use a graphing calculator because you can't do derivatives and integrals on your calculator. A formula card, again, 3x5, you can use both sides. And there are definitely some formulas you're going to want to write down. What you do not have to write down. You do not have to know any Taylor series. You do not have to know the Taylor series for sine or cosine or e or anything else. If I ask any question involving e to the x or sine x or cos x in the Taylor form, I'll say, here's the Taylor series or the power series for sine, cosine, e, whatever. Now I'm going to ask you to tweak it. You do not have to memorize those. Some of you may actually have committed them to memory because you've done them so many times. Okay, but I might say, here's e to the x. Now tell me, what is e to the 3x squared or something? And you know how to tweak it. You do want to write down things like the binomial formula. Okay, maybe you want to remind yourself, what's a geometric series look like? You're not going to be doing convergence and divergence of series, but I will be asking you for things like, what is the interval of convergence? So then you're going to do your tests, that sort of thing. You already know that. With the conic sections, okay, like before. Here's the equation of a parabola. Tell me all the stuff. Here's all the stuff. Tell me the equation of the parabola. Same thing with ellipse. Same thing with hyperbola. If it's a rotation of axes, main thing is, what is it? What is the angle? Okay, that's the main thing. For this stuff here, you probably want to write down the formula for the derivative of a parametric equation. See the dy dt and the dx dt, that's easy, but the second derivative is kind of tricky. What about the formula for the arc length? You might want to write that one down. It's not hard, but you may not have had it committed to memory because I believe that's the end of the material is the arc length stuff. Okay, so anyway, let's take a short break. If you have questions, please ask them today.